Hello friends, welcome back to my YouTube channel. In this class I am going to discuss 3 more problems of chapter 6 of P.K.NAG Engineering Thermodynamics, which are based upon the concept of second law of thermodynamics or Carnot cycle. In my previous 2 lectures I discussed about 10 problems, unsolved problems of chapter 6. In each lecture I discussed 5 problems. Now I am going to solve 3 more problems starting from 6.11 to 6.13 of chapter 6. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. So problem number 6.11 is like this. A heat engine operates between the maximum and minimum temperatures of 671 degrees Celsius and 60 degrees Celsius respectively, with an efficiency of 50% of the appropriate Carnot efficiency. That means we know that between given two temperature levels, the maximum efficiency of any heat engine is that of a reversible heat engine, and that is nothing but 1 minus sink temperature expressed in terms of Kelvin divided by source temperature expressed in terms of Kelvin. And the given heat engine, that is in this question, operates between the two temperature limits. Higher temperature limit is 671 degrees Celsius and 60 degrees Celsius, and with an efficiency of 50% of the appropriate Carnot efficiency. Carnot efficiency we can easily calculate 1 minus TL upon TH, and the efficiency of this particular heat engine is 0.5 of that, and it drives a heat pump which uses river water at 4.4 degrees Celsius to heat a block of flats in which the temperature is to be maintained at 21.1 degrees Celsius. You see, refrigerator and heat pump are the work consuming devices, and whatever work this particular heat engine produces is used to drive a heat pump. Heat pump is a device which transfers heat from low temperature to high temperature, and the primary purpose of this heat pump is to maintain a high temperature by continuously transferring heat to a high temperature reservoir. In this particular case, the low temperature is 4.4 degrees Celsius river water, and the higher temperature that is to be maintained to heat a block of flats is 21.1 degrees Celsius. This is the higher temperature. Assuming that a temperature difference of 11.1 degrees Celsius exists between the working fluid and the river water. In this case, what happens, there is a temperature difference between the working fluid and the thermal energy reservoir. But as far as the reversible heat engine is concerned, there is no temperature difference. Actually, whenever there is a heat transfer between finite temperature difference, that causes an external irreversibility. And in this case, that external irreversibility is there. So there should not be any temperature difference between the reservoir and the heat engine in case of total reversible heat engine. But in this case, the difference is there. On the other end, and the required room temperature on the other. On the both side, there is some temperature difference between working fluid and source and sink. 11.1 degrees Celsius is the difference. That's why the COP of this particular heat pump, which of course works on reverse Carnot cycle, but its COP is not the ideal COP, because of that external irreversibility effect of finite temperature difference between working fluid and the reservoir. So for that only, the actual COP of this particular heat pump is 50% of the ideal COP. Ideal COP is the COP of reversed Carnot cycle. Find the heat input to the engine per unit heat output from the heat pump. So why is direct heating thermodynamically more wasteful? So the solution is the problem is to be solved in this way. You see, the heat engine operates between The heat engine operates between two temperatures. 671 degrees Celsius is nothing but, in terms of absolute temperature, 944 Kelvin, and sink temperature is 60 degrees Celsius, that is 333 Kelvin. And heat engine, suppose, extracts heat. Of course, heat engine is a clockwise device. It extracts, let heat is in, it extracts heat q1 from high temperature reservoir and rejects, suppose, q2 to low temperature reservoir, and produces work, suppose w, produces work. Heat engine is a work producing machine, and this work is used to drive a heat pump. And heat pump is an anti-clockwise device, and it is a work consuming device. And heat pump transfers heat from low temperature reservoir, that is river, of 4.4 degrees Celsius, which is equal to 4.4 degrees Celsius is equal to 277.4 Kelvin. Let this heat be Q3. This heat that goes from this river to this working fluid or heat pump is Q3, and Q4 is suppose heat goes to high temperature reservoir, that is 21.1 degrees Celsius, that is 294.1 Kelvin. 294.1 Kelvin. So whatever work is produced by this heat engine drives this heat pump, and heat pump transfers heat from low temperature to high temperature with the expenditure of this work that is given by the heat engine. And another important thing that is mentioned in the question is, there is a temperature difference between the working fluid and the reservoir, which should not be there in case of a total reversible heat engine or heat pump. Whenever a heat engine or heat pump or refrigerator operates in a total reversible manner, there should not be neither any internal irreversibility effect nor any external irreversibility effect. And that heat flow between two finite temperature difference causes an external irreversibility effect, which is there. Therefore, the COP of this heat pump is not the ideal COP. In fact, that is 50% of the ideal COP as per the question. So you see, so temperature difference is 11.1 degrees Celsius. Temperature difference of 11.1 degrees Celsius is same as 11.1 Kelvin also. Temperature difference remains same, whether it is in terms of degrees Celsius or Kelvin. So this temperature, obviously heat flows in the direction of decreasing temperature. That means heat flows from high temperature to low temperature. Since there is a temperature difference between working fluid and this river end, and that difference is 11.1 degrees Celsius or 11.1 Kelvin. Obviously, suppose this is your working fluid temperature. So working fluid temperature will be less than this river temperature, because the heat is flowing in this direction. So that's why this temperature, the temperature of the working fluid, will obviously be less than the temperature of the river. So that is, if you subtract 11.1 Kelvin or degree Celsius from this temperature, you will find the temperature of 266.3 Kelvin. If you subtract 11.1 from 277.4, this is the temperature of working fluid at this end when heat is supplied to it. And if you calculate the temperature of working fluid when heat is transferred to it, temperature of working fluid while rejecting it when heat engine or heat pump rejects it. What is the temperature of working fluid here? Obviously it will be higher than this temperature by 11.1 degrees Celsius. So this temperature will be 294.1 plus 11.1, that is 305.2 Kelvin. Since heat always flows from high temperature to low temperature, so temperature at this end would be obviously higher than this 294.1, and as per the question, difference is same in both directions. So in at both points, here at the low temperature end and at the high temperature end. So that is 11.1 degrees Celsius. So this temperature at this point, the temperature of the working fluid is 305.2, and at this end when it is transferred to the heat pump, the temperature of working fluid is 266.3 Kelvin, and when heat is transferred from the working fluid or heat pump, then the temperature is 305.2 Kelvin. So now you see, the question requires you to find out if Q1 is if Q4 is 1 kilojoule, then what will be the value of Q1? That's what you are required to find out. If Q4 is, suppose, unit heat output, maybe 1 kilojoule or 1 joule, whatever you may take. Suppose we will take it 1 kilojoule. If heat extracted from the heat pump, this is the heat output of the heat pump. This amount of heat is extracted by the heat pump to the high temperature reservoir. So if Q4 is 1 kilojoule, then what is the value of Q1? By giving what amount of heat input to heat engine, we can produce 1 unit of heat output from the heat pump. So is it less than 1 kilojoule we have to give, or more than 1 kilojoule we have to give, or equal to 1 kilojoule we have to give? That's what we are required to find out. And as per the given data, you see, efficiency of reversible heat engine that operates between these two temperatures is efficiency of reversible heat engine that operates between 671 degrees Celsius and 60 degrees Celsius, obviously is 333 divided by 944, that is equal to 0.64725. So what is the efficiency of actual heat engine? As per the question, the efficiency of the heat engine is the 50% of the Carnot efficiency, and this one is Carnot efficiency. So efficiency of actual heat engine that operates between two given temperatures is equal to 0.5 multiplied by 0.64725, that is equal to 0.323623. And you know, efficiency of any heat engine is 1 minus heat rejected by heat added. Efficiency of any heat engine, be it reversible or irreversible, reversible के लिए 1 minus sink temperature in terms of Kelvin divided by source temperature expressed in Kelvin, that can be applied. But for any heat engine, be it reversible or irreversible, efficiency will be 1 minus heat rejected. In this case, heat rejected obviously is Q2. Q2 is the heat rejected, and Q1 is the heat supplied to the heat engine. So 1 minus Q2 divided by Q1 is equal to 0.323623, or Q2 by Q1 is equal to 1 minus 0.323623, that is 0.6764. So now coming to the heat pump, you know, COP of the ideal COP of this heat pump would be ideal COP. That means had this operated as a Carnot refrigerator heat pump, then what would have been the COP? That is the ideal COP. if there would be no difference between the no temperature difference between working fluid and the reservoir at this end and also at this end, that if the temperature of working fluid is same as the temperature of reservoir, what would have been the efficiency? So ideal COP would be the temperature to which heat is supplied by heat pump. That's what we calculate the COP, ideal COP. COP of a reversed Carnot heat engine or Carnot heat pump. So that will be 305.2 divided by the temperature difference between these two points. At this point the temperature of working fluid is 305.2 and here the temperature is 266.3. That difference 305.2 divided by 305.2 minus 266.3. So this is equal to 7.866. 7.866. This is the ideal COP. But as per the question, the actual COP is the 50% of ideal COP. The actual COP is the 50% of ideal COP. So actual COP is equal to 0.5 multiplied by 7.866, that is 3.923. And actual COP is nothing but the actual COP of any heat pump or heat pump will be desired effect by work input. In this case, desired effect is to continuously supply this heat to the higher temperature side or high temperature body, that is Q4, and work input is W. Had this been operated as a refrigerator, COP would have been Q3 by W, not Q4 by W. And COP of this heat pump is Q4 divided by W. And if it had been a refrigerator, its COP would have been Q3 by W. So actual COP is equal to 0.5 multiplied by 7.866, that is equal to 3.923, and is equal to desired effect by work input Q4 divided by W. Q4 divided by W. Actual COP will be Q4 divided by W. Q4, as per the question, we are required to find the value of Q1 when Q4 is 1 kilojoule. So if Q4 is 1 kilojoule, then W will be how much? From this I can find out 3.923 is equal to Q4 by W. It means 3.923 is equal to 1 by W, 1 kilojoule by W. From this W I will find out 1 by 3.923 kilojoule, that is 0.2549 kilojoule. So W is nothing but Q1 minus Q2. Since we are to find out the value of Q1 only, given the value of Q4 is 1 kilowatt, if heat pump supplies 1 kilojoule, I will take in form of energy, not in terms of power. Suppose Q4 is 1 kilojoule, then this will be kilojoule. 0.2549 kilojoule. So we are required to find out value of Q1. What is the heat supplied to the heat engine? So Q1 minus Q2 we are required to find out is equal to Q1 minus Q2 is nothing but from this Q2 is nothing but 0.676 for Q1. Q2 is 0.676 for Q1. Putting this value of Q2 here, 0.6764 Q1. This is 0.3236 Q1. Since already we have found out the value of W by putting that 0.2549 kilojoule is equal to 0.3236 Q1. So Q1 will be 0.2549 divided by 0.3236, so kilojoule. So this is equal to 0.7877 kilojoule. So that means on supplying 0.7877 kilojoule to the heat engine, on supplying an amount of 0.7877 kilojoule of heat to this heat engine, we are able to extract 1 kilojoule of heat from a heat pump. So in fact, more heat is produced by this heat pump from a less amount of heat. On the other hand, if we had used direct heating for this maintenance of this high temperature, suppose if we had used resistance heating. In resistance heating, what happens? In resistance heating, if we supply suppose this is a resistance, and if you supply suppose 1 kilojoule of electrical energy, the heat produced will be 1 kilojoule only. But in this case, you see, on giving 0.7877 kilojoule of heat into this particular heat engine, we are able to get this 1 kilojoule of amount of heat, which is more than this 0.7877 kilojoule. That means heat pump, by consuming this work produced by this heat engine, can extract or supply 1 kilojoule of heat. But at the same time, what is the energy consumed, what is the heat supplied to the heat engine? That is 0.7877 kilojoule. So that means it is a thermodynamically we are in an advantageous position. It is an efficient process. But if you had used direct heating of, for example, resistance heating, it is a wasteful process, because here on supplying 1 kilojoule of electrical energy only, we are producing 1 kilojoule of heat energy. But in this particular case, heat engine and heat pump combination, what we see is, on supplying less than 1 kilojoule of heat to heat engine, we are able to produce 1 kilojoule of heat. So this is a thermodynamically efficient process. So next question is like this. 6.12, an ice making plant produces ice at atmospheric pressure and at 0 degrees Celsius from water. The mean temperature of the cooling water circulating through the condenser of the refrigerating machine is 18 degrees Celsius. Evaluate the minimum work in a kilowatt hour required to produce 1 ton of ice. The enthalpy of fusion of ice at atmospheric pressure is 333.5 kilojoule per kg. So here, ice is being produced from water. So it works on the principle of refrigeration. You see, on extracting or removing heat from water, we can produce ice. So this ice plant, the primary function of this ice plant is to remove heat from the water so that we can obtain ice. So this is quite similar to what happens in refrigerator, principle of refrigeration. You see, the low temperature in this case is 0 degrees Celsius, that is 273 Kelvin, because ice will be produced from water at 0 degrees Celsius and atmospheric pressure. And the higher temperature to which the heat is to be supplied is, that is the condenser end. In case of refrigerator, evaporator, compressor, condenser and expansion valve. In evaporator, heat is to be removed from the cold space, and in condenser heat is rejected to a high temperature surroundings. So in this case, the temperature, high temperature is mean temperature of the cooling water circulating through the condenser is 18 degrees Celsius. So this is the high temperature, and 18 degrees Celsius surrounding temperature is equal to, in terms of Kelvin, 291 Kelvin. So minimum electrical work is required to find out. We know that the refrigerator is a work consuming machine. Refrigerator is a work consuming machine. So, and the least work is consumed by a refrigerator if it operates in a reversible manner, and the maximum work is produced by a heat engine if it operates in a reversible manner. So you are required to find out the least or minimum electrical work. That means you have to find out the COP of the reversed Carnot cycle. In this case, refrigerator and heat pump, when operate on a reversible manner, means they operate on reversed Carnot cycle. So I have to find out the COP of reversed Carnot refrigerator that operates between this low temperature 0 degrees Celsius and high temperature 18 degrees Celsius. So suppose this heat is Q1, it is removed by the refrigerator continuously. So how to produce ice? How to produce ice means we have to consistently or continuously transfer heat from this low temperature and supply heat to this high temperature. The principle of refrigeration means refrigerator is a device which continuously extracts heat from low temperature space to high temperature space to maintain the temperature of that particular space at a lower level than that of the surroundings, because no matter whatever insulation you put, there would be some leakage, and heat will always flow from high temperature body to low temperature body. So if heat flows to this space, then suppose Q1 heat flows to this space, same Q1 heat has to be removed by the refrigerator so that the temperature will be maintained at this point, and ice could be produced. Ice could be produced by extracting heat from this. So that's why, suppose this is the heat that is uh, to be removed, Q1. So W is the work input. W is the work input. So the minimum work input has to be required. So maximum COP in this case is maximum COP. Maximum COP is, or ideal COP is, as I have already discussed, is, in this case the ideal COP is this temperature divided by temperature difference between these two. Of course the temperature is to be expressed in Kelvin only. So COP of reversed Carnot Carnot refrigerator is 273 divided by 291 minus 273. That is equal to 15.166. This is the maximum COP. And COP of any refrigerator is desired effect by work input. COP of any refrigerator is desired effect by work input. In this case, the desired effect is removal of heat from low temperature body, that is Q1, and work input is W. So Q1 by W, COP of any refrigerator. But in this particular case, since minimum work is required to be found out, and minimum work input is required when the COP is maximum, so I can say COP maximum is possible only when, for the given heat removal, क्योंकि हमको 1 ton ice produce करना है, we have to produce 1 ton of ice, so that and 1 kg of ice, latent heat enthalpy of fusion of ice at atmospheric pressure is 333.5 kilojoule per kg. So on removing this heat from 1 kg of ice only, 1 kg of water only, we can produce ice. So that Q1 is constant, because since we are required to find out minimum work to produce 1 ton of ice, 1 kg of ice can be produced if we remove 333.5 kilojoule amount of heat. So Q1 is fixed, and COP maximum we just calculated, and it is 15.166. So W minimum can be calculated from this. Once you have calculated Q1, then COP maximum has already been calculated, and it is 15.166. So Q1 is how much? Q1 is heat to be removed. Heat to be removed to produce 1 ton of 1 ton of ice. 1 ton of ice means 10 quintal, or 10 into 100, that is 1000 kg. 1000 kg. And as per the question, 1 kg of ice, 1 kg of water, the amount of heat that is removed from 1 kg of water to convert it into ice is 333.5. 333.5. So for producing 1 ton or 1000 kg, what is the amount of heat to be removed? Q1 is, suppose, 1000 multiplied by 333.5 kilojoule. To produce 1 kg of ice, we need to remove 333.5 kilojoule. So to produce 1 ton or 1000 kg of ice, we need to remove this much of heat. And COP maximum is 15.166, and this is equal to 333.5 multiplied by 1000 divided by W minimum kilojoule. W minimum kilojoule. So from that we can easily calculate W minimum. What is the minimum work required? W minimum is equal to from this, W minimum is equal to this into this divided by this. 333.5 multiplied by 1000 divided by 15.166 kilojoule. If you are required to find out, if you want to find out in terms of kilowatt hour, I can easily convert this into kilowatt hour, because you see 1 kilowatt hour is equal to 1 kilojoule per second. 1 kilowatt is nothing but 1 kilojoule per second, and on 1 hour is nothing but 3600 second, and this is equal to 3600 kilojoule. So W minimum work input required is equal to 333.5 into 1000 divided by 15.166 into 3600. This much of kilowatt hour. This is equal to 6.108 kilowatt hour. So this minimum, this amount of work is required. If the cycle operates in a reversible manner, this is the work input required, and this work input is minimum. So next question is 6.13 is a reversible engine works between 3 thermal reservoirs A, B and C. The engine absorbs an equal amount of heat from thermal reservoirs A and B kept at temperatures TA and TB respectively and rejects heat to the thermal reservoir C kept at temperature TC. The efficiency of the engine is alpha times the efficiency of the reversible engine, which works between two reservoirs A and C. Prove that this is equal to TA by TB is equal to this much. So now a reversible heat engine operates between three reservoirs. A reversible heat engine operates between three reservoirs. Suppose this is suppose the temperature of reservoir A is TA and it extracts. So another reservoir, high temperature reservoir, is it extracts equal amount of heat from thermal reservoirs and B kept at temperatures TA and TB. Suppose the temperature is TB, high temperature. Let heat that is extracted by this heat engine is Q1 from high temperature reservoir, and this heat is also Q1 because in the question it is given that it absorbs an equal amount of heat from the thermal reservoirs A and B. So heat extracted is same both from TA, the temperature TA heat extracted is Q1 let, and from TB heat extracted is Q1. So this is the heat engine. Let heat rejected by this heat engine is Q2 and heat rejected here is Q3 suppose. And this temperature is TC. TC. So now what is the efficiency of this heat engine? Reversible engine we have to calculate, and it is given that whatever is the efficiency of this heat engine, it is alpha times the efficiency of a reversible heat engine that operates between TA and TC only. If a reversible heat engine operates between temperatures TA and TC only, then its efficiency will be 1 minus TC divided by TA. We know that. And if the efficiency of this reversible heat engine, alpha multiplied by 1 minus TC upon TA. So I can write down efficiency of this particular given heat engine is alpha multiplied by 1 minus TC upon TA. This is written in the question. The efficiency of the engine is alpha times the efficiency of the reversible engine, which works between the two reservoirs and C. So this is what we are now to find out. What is the efficiency of this heat engine? So for that we are to find out, for this case you see Q1 divided by TA is equal to Q2 divided by TC. Q2 divided by TC, because heat supplied by the according to the thermodynamic temperature scale, heat coming from this temperature is TA. So Q1 by TA is equal to Q2 upon TC, because TC is the temperature of heat rejection. And for this case, Q1 by TB is equal to Q3 by TC. Q3 is the heat rejected to the low temperature reservoir TC here, and Q1 is the heat supplied from the TB, high temperature reservoir. Since in both the cases heat supplied is same, Q1. So that's why here it is Q1 and here it is also Q1. From both these relations, we can easily calculate the value of Q2 and Q3. So Q2 from this expression will be Q1 multiplied by TC upon TA. And from this Q3 is equal to Q1 Tc upon Tb. Tc upon Tb. Tc upon Tb. So efficiency of this heat engine will be 1 minus heat rejected divided by heat added. Q2 plus Q3 divided by, here the heat rejected to the low temperature is Q2 and Q3, but heat added to heat engine is Q1 plus Q1, since it extracts equal amount of heat from T and TB. It is given in the question. So heat supplied is Q1 plus Q1, that is 2Q1. So if I use this value, if I substitute the values of Q2 and Q3 from these equations, this will be 1 minus Q1 Tc by Ta plus Q1 Tc upon Tb divided by 2Q1, that is equal to 1 minus Q1 Tc 1 by Ta plus 1 by Tb divided by 2Q1, that is cancels out Q1. So 1 minus Tc by 2 1 by Ta plus 1 by Tb. This is equal to 1 minus Tc by 2Ta minus Tc by 2Tb. 2C by 2Tb. And as per the given information in the question, this is equal to alpha into 1 minus Tc upon Ta. Alpha 1 minus Tc upon Ta is this much according to question. This is 2Ta minus Tc upon 2T. So I can write like this: alpha minus alpha Tc upon Ta is equal to this much, 1 minus Tc upon 2Ta minus Tc upon 2Tb. So you see, the expression that is to be proved is Ta by Tb and Ta by Tc is here. Ta by Tb has to be brought. Ta by Tb. So how can I bring in Ta by Tb in this expression? Only by multiplying both sides by Ta upon Tc. I get alpha Ta upon Tc minus alpha, because Tc by Ta on being multiplied with Ta by Tc, it is 1. So it is equal to Ta upon Tc minus 1 by 2 minus Tc upon 2Tb on being multiplied by Ta upon 2C. Ta divided by 2Tb. Tc by 2Tb on being multiplied by Ta by 2Tc, I will get Ta by 2Tb. And this is, but we are to prove that Ta by Tb is equal to this much. So I will bring Ta by Tb to one side. So so if I bring this to one side, that will be half Ta upon Tb is equal to Ta by Tc minus alpha Ta by Tc. Alpha on being brought to this side will be plus alpha minus 1 by 2. On multiplying both sides by 2, I will get Ta upon Tb is equal to 2ta by 2tc minus alpha 2 alpha ta by tc plus 2 alpha minus 1. 2 into alpha minus 2 into 1 by 2, that is 1. So this is equal to, I can write 2 alpha minus 1, 2 alpha minus 1 plus 2 into 1 minus alpha, 2 into 1 minus alpha ta upon tc. Sorry, this is 2ta by tc only. So 2 alpha minus 1 plus 2 minus 2 alpha, 2 minus 2 alpha, that is 2 into 1 minus alpha ta by tc. So that is what we have to prove, that is ta by tb is equal to 2 alpha minus 1 plus 2 into 1 minus alpha ta upon tc. That's all. Thank you for watching.